So yes, welcome to this week's Origins Colloquium. It's a pleasure to have Jin Koda giving us the talk this week. So Jin received your PhD from University of Tokyo, if I'm correct.
Yeah,
And
many
then,
years ago.
yeah, well, what year was that, Jin?
I think 2002,
2002. Okay.
if I
Then
remember it correctly.
then you were at NRO, that's Nobayama, I guess, for a postdoc, and
Uh-huh.
then Owens Valley, and then which became Karma, and
Mhm.
then Caltech. I think that's where I first met you when you were at
Yeah.
Caltech, working with Nick Scoville,
Mhm.
and then you became an assistant professor at Stony Brook. In what year was that, Jin?
2009.
2009. Okay, where you are now a professor there. So that's great. And Jin has worked on a range of topics in the interstellar medium and galaxies. And today will tell us about his thoughts on giant molecular cloud lifetimes, one of the problems that's been around for many decades. So please go ahead, Jin.
Okay, thank you very much for the introduction and the invitation. Yeah, so I gathered that this meeting, this colloquium is more for discussion rather than, presenting results. So I brought some discussion point on the lifetime of molecular clouds, which has been the topic of interest for almost like 50 years or so. So, I think most of you probably know about molecular clouds, which are dense concentration of molecular gas. And if you look through the Milky Way disk, you find something like 3,000 or 5,000 of them. Typical diameter of molecular clouds, giant molecular clouds, are something like 40 parsecs, and their masses are 4 times 10 to the 5 solar masses. And then the average density within the cloud is something like 300 particles per cc. And you think about the average density of galactic ISM density in the galactic disk, which is about 1 particle per cc. So it's about 2 orders of magnitude enhancement in density. And of course, it's the site of star formation. So he wants to know about star formation. He wants to learn about star formation, and then the evolution of molecular clouds. The lifetime of molecular clouds are very important. And as I said, this has been the topic discussed for over almost 50 years. And there's a range of cloud lifetime suggested. And some people say it's extremely short, a few million years. And some other people say it could be very long, 100 billion years or even longer than that. And I think most people are somewhere in between, something like 10 to 30 million years is the lifetime of molecular clouds. And cloud lifetime is, of course, important for star formation. And if you think about lifetime in the context of galactic rotation, the consequence is significant. So in the Milky Way, at the distance of the sun, the radius of the sun, the rotation time scale is something like 200 million years. And if a cloud lifetime is a few million years, and that means cloud form and then die almost immediately without moving much, almost at all, within the disk of a galaxy. And if the cloud lifetime is 10 to 30 million years, which is roughly the spiral arm crossing time scale. So maybe the gas gets condensed or compressed when it gets into spiral arm, becomes molecular clouds, and then form stars, and their stars, their feedback basically disperse the molecular gas and molecular cloud. And when the gas gets out from spiral arms, then you see atomic hydrogen, not molecular clouds. That's 10 to 30 million years. And if the cloud lifetime is 100 million years or even longer, and then the cloud as entity, move around the galaxy. Okay. And this discussion, I brought some discussion point about short cloud lifetime, but before getting into that, I want to make one point from the long cloud lifetime camp. So what they say, well, actually including myself, is the absence of atomic hydrogen in the inner part of the galaxy. So if a molecular cloud lives short and then gets dispersed in short time scale, then we should be able to find the remnant of molecular cloud or molecular gas, which should be atomic hydrogen. And atomic hydrogen, we can, of course, observe using 21 centimeter emission, and we don't find much. So most of the gas is in the atomic phase in the Milky Way and other substantial spiral galaxies like the Milky Way. And because of that, the gas needs to stay molecular, and the lifetime of molecular clouds and molecular gas should be long. And that's an argument from long lifetime camp.
Well, Jin, did you just say most of the gas is in? You said atomic, but I think you meant molecular.
Yeah, I meant molecular. Sorry. Yeah, that's right. So most of the gas is in the molecular gas. So this is a plot from the analysis of the Milky Way, and y-axis is molecular gas fraction, molecular gas mass divided by the total mass, H2 plus H1, as a function of galactic radius. And then in the inner part, most part of the disk, the molecular gas fraction is high, more than 50%, more like 70 or 80% or so. And also, if you look at the single radius, the scalar is the spiral arm, inter-arm variation of molecular gas fraction. And even in inter-arm regions, the molecular gas fraction doesn't change that much, something like 20% or so. It does not go down all the way down to zero, which is the case if molecular clouds die immediately after spiral arm passage. So that I think is a very basic observational fact. We just don't see atomic gas in the inner part of the galaxy. But a recent trend is for short cloud lifetimes. And there's a nice review, a very recent review by Eva Schinnerer and Adam Leroy from this year in annual review series you can find in AstroPH. And they summarized 3 methods to estimate cloud lifetimes. And I'm going through each of them in detail, but just briefly. So the first one is about demographics of clouds with and without star formation. They look at the molecular clouds and ask if each cloud has star formation or not. And the second method is from spatial correlation of molecular clouds and star formation. And then the third method is the cloud evolution along gas flows. And here's the talk outline. So I'm going to explain each of them in the order of C, A, and then B. And after explaining each method, I raise some discussion point. So the first one, I start from number C, molecular cloud evolution along gas flows in the galaxy. So this started from the observation about 10 years ago, or even 15 years ago, a precursor of Fang's survey using Plato-Review interferometer. And this is an observation of M51 in CO120 emission. And they found molecular clouds on spiral arms and also in the inter-arm regions. And they also found a trend that as you move away from spiral arms, then the population of molecular cloud decays. So if you have, you have 2 spiral arms and inter-arm region in between, and then the population of molecular clouds decline as you move away from the previous spiral arms. So if you measure the distance of this typical distance of this decay, divide that by the rotation velocity, and then you can get some kind of lifetime. You can get lifetime of molecular clouds. So they did that in 2015, and in this case, they divided angular separation by angular speed, which basically is the same thing, and got the cloud lifetime of 20 to 30 million years. But a few years ago, I looked back, and this discussion was the start of a recent discussion for short cloud lifetime. But I looked back at their paper recently and realized that they didn't include one term in this calculation. So they are measuring the distance from spiral arms, and the spiral arm is, of course, rotating around the galactic center. So what they should think about is the velocity or angular velocity with respect to the spiral arm pattern. So we should subtract spiral arm pattern speed from rotation velocity. So I just took their table And then pattern speed they measured a few years before this 2015 publication. So I just took their value and then recalculated the time scale, and that gives me 60 to 500 million years or so. So this small correction makes the cloud lifetime very long. The second method is about the demographics of molecular clouds with and without star formation, which was first done by Kawamura et al. So this is right panel is a plot of H2 region, H alpha image, and contours CEO, so molecular clouds. As you can see, some molecular clouds have star formation H2 region associated with it. Some molecular clouds do not have H2 region associated with it. So they counted the number of molecular clouds, classified molecular clouds into type 1, 2, 3, depending on the phase of star formation. So type 1 cloud have no star formation, it's just molecular clouds, no H alpha emission, no young clusters around it. Type 2 cloud have H2 regions very nearby, and then type 3 cloud have H2 regions and young clusters. So by the number count, they found the ratio 24% and 50% and 26% for each type. And now, if you know the time scale of any of these phases, then you can translate this population into the duration that the cloud spend in each phase. And in their case, they aged young cluster population that they found around molecular clouds, and they found something like 7 million years for type 3 phase. And from this ratio, they can translate that into the time scale that clouds spend in each phase. And if you add them up, you get cloud lifetime of 20 to 30 million years. Again, a relatively short time scale. But you may realize that it's actually, the short lifetime scale is actually an assumption rather than a result, because a molecular cloud could go back to type 1 phase after star formation. So even if a cloud starts from no star formation and then start star formation and have young clusters, after that, if they go back to type 1, then it still maintains the fractions demography fix of cloud population, but the cloud lifetime becomes much longer. So if it goes through like 3 cycles of star formation, for example, and then the cloud lifetime becomes 3 times 20 to 30 million years, and that's already 100 million years, very long lifetime. So 2 of the 3 argument for short lifetimes, we can easily come up with counter arguments. So the third one is spatial correlation between molecular cloud and star formation or star forming regions. And this one is a little bit difficult to explain. So I want to go back to the beginning, go back some history. So the first motivation of this analysis, tuning fork analysis, we call it, is to determine the correlation spatial lengths between molecular gas and star formation for the Kennigat-Schmidt study. So for Kennigat-Schmidt relationship, what people do is take something like 1 kiloparsec aperture and then put it on top of some part of a galaxy and measure average gas density and average star formation rate within this 1 kiloparsec aperture, and correlate the two, and you find nice relationships. But if you use smaller and smaller aperture, let's say 10 parsecs aperture or 100 parsec aperture, then you start to see separation between molecular clouds and star formation. So they wanted to find at what size scale or aperture scale they start to find nice correlation between molecular gas and star formation, H alpha emission. So they took H alpha and CO data, in this case M33, and then put an aperture on top of either gas or molecular cloud peak or H2 region peak. And they changed the aperture size starting from small to large. and measured CO emission within this aperture and H alpha emission in this aperture, and calculated the ratio between the two. So CO flux over H alpha flux within an aperture. The x-axis is the aperture diameter, and they change the aperture size from small to large. If you go to very large scale, and then you start to find galactic disk average, right? So they converge. So sorry, the top branch is aperture on top of CO or molecular cloud. And then the bottom branch is the same thing, FCO over H alpha, but the aperture is on top of star-forming regions. And if you have aperture on top of molecular gas, small aperture may not include H alpha emission, but if you increase the aperture, you start to find surrounding H2 regions. And that's why you start from very high value, a lot of CO over H alpha, and then it goes down. And if you put aperture on top of H2 region and increase the aperture size, at the beginning, you don't find much CO, and that's why you start from low value. But as you increase the aperture size, you start to increase more and more CO emission. And at some point, you get the average CO to H alpha flux ratio of the entire galaxy. And that's this point. Okay? So the correlation length is what they are shooting for. And then there are a group of theorists, Derek Cruisens, and very smart person. So he came up with an idea that this entire shape of the tuning fork can be explained by molecular cloud life cycle. So the cloud life cycle they had in mind is something like this. So molecular cloud form and then live for the duration of T gas. And near the end of its lifetime, at the middle of its lifetime, it forms stars, and gas and stars coexist for some duration of time, which they call T overlap between gas and star. And then molecular clouds die, and then stars survive, and the lifetime of stars is T star. Okay, so that's the lifetime they have in them in mind. Now I go through some detailed probability calculations. So stay tuned. So listen carefully. So we put an aperture on top of gas or star, right? And now we split that aperture into smaller cells, grids. The size of the aperture is L, and then the size of each grid is lambda. And with this setup, the number, and if you put aperture on top of a gas particle molecular cloud, then the number of grids or cells within an aperture is something like L over lambda squared. That's the number of cells within an aperture. And in each grid, some grids don't have a star formation or gas, and some grids have gas or stars. So the fraction of the grid or cells that have star formation, which is basically the density of star-forming regions, is eta. And if you multiply eta and n, then it gives you the number of cells which have either stars or gas, so involved in star formation. Good? Now, we want to calculate, since we measure the flux, H alpha and CO flux within an aperture, we want to calculate flux in CO or gas, or in H alpha or star formation. So with this number of grids, the number of clouds in this cell is this value, which is the number of cells which have either gas or star formation, or stars, H2 regions. And fraction of the cells, among that, the fraction of the cells which have gas is, the probability is T gas over T total. T total from here to here. Do you see my cursor, by the way?
Yes, we do. Yeah.
Okay, good. So from here to here, T total is the whole time scale. And in that time scale, T gas is the duration that a cell can have the gas particle. So T gas over T total is the probability for each cell to have gas particle. So the second term is the number of cells which have gas. We put the aperture on top of one gas particle, so we add one here. So within the bracket, that's the number of cells which have cloud. And if you multiply typical flux of gas particle, either CO flux or any other tracers, then you get the flux within the aperture. Good. For stars, we do the same thing. And again, we have aperture on top of gas particle. So the number of cells within an aperture, the number of cells which have star particle is eta n, which is the total number of cells which with either gas or stars. And the fraction of that with stars is T star over T total. So we multiply that, and that's the number of cells which have star particle. The central cloud may or may not have stars, and the probability is T over T gas. And if you multiply the the average star flux, either H alpha flux or 24 micron UV, whatever tracer you want to use, the flux of that is multiplied, and that gives you the total flux, star flux within the aperture. So if you divide one by the other, you can get this relationship. So divide one by the other, and then also normalize the whole thing with galactic average. And then you get this equation. So what you measure the ratio of flux is basically written with the time scale ratios and also the aperture size. And we can do similar calculation for an aperture with star at the center, and then come up with the equation. So this upper branch and bottom branch, they can be described with this equation. So from observation, you get data point of the tuning fork, and you fit these two equations, and that gives you the time scale ratios. And if you know any of these time scales, then you can separate them and then derive lifetime of molecular cloud and overlap time scale of gas and stars, and also the total duration, and also the length scale of correlation. So the Fangus team applied this method to their data, large sample of galaxies, and found that cloud lifetime, something like 5 to 30 million years, the short size of cloud lifetime. So that's the situation right now. And last year, Jonathan and I encountered in one of the conferences, the one in Lyon, I think, and we decided to write a simple short paper on the tuning fork analysis. The tuning fork paper is very long and convolved, and we wanted to make a point in a short paper. So their model is something like this. The cloud have lifetime and start, and then live as it is, and then form stars, and live with stars, and then die, and what's left is stars. And all of these are the timescales to characterize that. And to reproduce their model, we came up with this extremely simple setup. So what we did was just put 1,000 gas particles in a disk with radius of 5 kiloparsecs. So this is the distribution, blue points. And each of them have a constant flux because, different fluxes are too complex. So we just set it constant. And in reality, they could move around in the galactic disk, but if their lifetime is short, they don't move at all, move much in a disk. So we assumed that they don't move. And their lifetimes are 30 million years. And they occasionally form stars, and the probability is delta t, which is the time step of our time evolution simulation over T gas, the cloud lifetime. And star formation doesn't change the mass of the cloud or flux of the cloud. And clouds die and disappear after 30 million years. But to maintain the same number of cloud particles, we just redistribute them somewhere randomly in this disk. And once star particle is formed, they live for 20 million years, and they also have constant mass and flux, and they stay with their parental clouds for 5 million years, which is this overlap period, and then drift away. And we set drift velocity, which could be any number, but we just picked 10 for the initial set of simulations, and they move in random directions. There's no stellar feedback. So it's very simple. You have a bunch of gas particles, and they occasionally form stars, and then stars live with the gas particle, and then gas dies, and then stars drift away. We just simulate that. It's very simple. So this is a demonstration that this simple model just works for the tuning fork analysis. So this is exactly what I explained. Blue points are gas particles, and they occasionally form stars, and stars live together with the parental gas for T over time scale, and then move away, the parental clouds die. And we can fit the tuning fork equations. So here are the input parameters, and these are the output parameters after the fit. So the fitting, gives roughly the correct time scale, correct answer. So the model seems to work. So now we stretch this model and say that, okay, clouds never die. They are immortal. They just live forever, okay? And instead of cloud death, they just repeat the same process again and again. So the clouds start the phase, and they just live alone, and then form stars and live with the stars for some time, T over the time scale, and then the stars drift away from the parent clouds, and then the clouds start the new cycle, but they never die. So in the context of the previous slide, what's changed is this cloud lifetime is now duty cycle of molecular cloud, star formation duty cycle of molecular cloud, 30 million years. And then instead of they die and disappear, they just live forever in this simulation. And with this setup, we can also reproduce the tuning fork plot nicely. And here are the input parameters, and here are the output parameters. The tuning fork analysis, gives you reasonable time scale, which is not the cloud lifetime, but it's just the duty cycle of star formation in forever living molecular clouds. So this shows you that the tuning fork diagram, the tuning fork analysis, which is based on beautiful theory, probabilistic theory, which gives you some time scale, but it doesn't necessarily mean that what returned is the cloud lifetime. I think in the past 7 to 10 years, in almost every conference we go about star formation and the interstellar medium, we heard about tuning fork analysis. And because of the beauty of the theory, I think we are just impressed and accepted the idea that it traces molecular cloud lifetime. But we found that even for immortal clouds, almost any parameters, we can reproduce the tuning fork. We can generate tuning fork pattern, and we can fit it, and we can get star formation duty cycle as the return of the tuning fork fit. Okay, I think I passed the time. Is it okay? Can I spend a few more minutes?
Yeah, a few more minutes is fine, up to 5 more minutes, say. Okay,
good. Okay. Yeah. So I said that almost any parameters we can generate tuning fork pattern, and we can fit it reasonably and get star formation duty cycle instead of cloud life cycle. But there's one thing which is necessary for this model, which is stellar drift. And stars have to drift away from the parental molecular clouds if clouds live forever. because otherwise stars are always on top of clouds, and you shouldn't find any H2 region away from molecular gas. So in the context of tuning fork graph, this is the comparison of modal clouds and immodal clouds with drift velocity of 0 and 5. And if the clouds are modal, even the drift velocity is 0, clouds just die, so you can find stars without parental molecular gas. But in case of immodal cloud, if stars don't drift away, then when you find a star or when you put the aperture on top of star particle, then you always find a gas particle associated with it. So the bottom, what we find with zero velocity for immodal cloud is this flattening of blue points, the gas at the center. It's easiest to explain from the bottom branch. So bottom branch, if you put aperture on top of stars, you always find the gas particles. So the ratio is the ratio of the flux ratio of each molecular cloud. And it's constant until your aperture starts to include molecular gas without star formation. Blue points, the aperture is very small, but you still sample molecular cloud with and without star formation, the general population nicely. So even the aperture is small, the ratio you get is the average ratio over the entire disk. So that's why even if you change the aperture size, it stays constant. And that's the big difference between modal cloud and immodal cloud. If we add drift velocity, small drift velocity, then the small aperture part changes because now cloud and stars move away from each other. So it changes the statistics with small aperture. Sometimes aperture don't find H2 region next to it, within it. Sometimes it does. But if you move to larger and larger aperture and beyond the maximum drift distance, then you find the same thing, the top branch flattened out. And this flattening out point is exactly where you expect from drift length. So drift length is drift velocity times the drift time scale, and in this case, it's 76 parsecs. And then flattening happens with the aperture, diameter 152 parsecs. And that's because if the aperture becomes larger than the maximum drift velocity, you always find gas and stars associated. So it's basically go back to this situation. So this flattening point could indicate, could choose which modal or immodal clouds are correct. And this is just manually doing so, but I went back to the Fang's paper. This is observational data. And if you look at it, you often find this flattening in many observed spiral galaxies. And I think Zena is analyzing it. This is part of what she is doing. But from the exact shape of tuning fork pattern, we may be able to constrain whether modal or immodal cloud models are correct. Okay, so I have several more slides, but I can finish here. So there are a few evidence that people are talking about for short cloud lifetimes, and I'm not going to say that which lifetime is correct. I just want to bring some discussion points. So the three methods summarized in the very recent review, all of them we can easily come up with counter arguments. And these counter arguments are not complex at all. I'm just saying that after this phase, the cloud could go back to this, and then you can explain the observation, and the cloud lifetime doesn't need to be short. So the question is, for discussion point is, do we really have evidence for short cloud lifetimes? Okay, I can stop here.
Very good. Thank you very much, Jin. And of course, you can show slides in the discussion if they are relevant, of course. And
okay.
So let's open up the presentation for discussion. If you have questions in the Zoom, raise your hands, please. And I'll look also here. So, John, please.
Hey, Jen, very, very interesting summary here. I was wondering if anything could be learned if you look at galaxies that are basically red and dead but have molecular gas. Do you think you could learn something about cloud lifetimes by looking at a place that is not actively taking place in star formation? And what can we derive about that?
Yeah, that's a very good point. Yeah, so there must be some environmental difference. And so even within the Milky Way, if you look at the inner disk, then it's almost completely molecular. But if you look at the outer disk outside of the solar circle, then the H1 is dominant, and you see molecular cloud only around spiral arms. So in those environments, the cloud lifetime could be shorter. Um, so yeah, looking at the dead galaxies, different environment, that could, give us a clue to the cloud lifetime. There may not be just a single cloud lifetime for all environments. It could vary depending on the environment. If you look at dwarf, for example, the lifetime could be different. Or if you look at, elliptical galaxies, it could be different. Outer part of the galaxy, it could be different. Most of the things I said in this talk is about the inner disk of spiral galaxies, like the Milky Way.
Let me just follow up on that. So you say in the outer region, you said that they're only in the spiral arms. So there is inner arm molecular gas. Would you
Mhm.
say that yes, there is, but they're not clouds?
So we do find, so there is some evidence that they are molecular clouds, and we can detect them in CO. But the vast majority of the gas in the outer part of the galaxy or outside of the optical disk is atomic. So in that environment, cloud lifetime could be different from the inner part.
Gene has a
Thank
question,
you.
but let me follow up on that then. So if you do the tuning fork, but restrict the area analyzed to only be the outer
Mhm.
galaxies, parts of galaxies, does the answer change then? Has anyone done that?
I don't think anyone have done that. The reason is there's not much data. So FANGS covers inner part of the disk. Um, and there's not much CO observation of the outer disk where H1 is the dominant component.
Well, you just have to do the outer annulus you can do with the current data.
Yeah, that's right. So yes, we can do it. I don't think anybody has done it. Yeah.
Mm-hmm. And so we'll come to Gene in a second, but I know, Jin, you have worked on arm, interarm, and molecular gas fraction. Can you say a little more about that and the implications for the impact of arms in forming the clouds?
Yeah. So you are talking about this?
Right, but I
Yeah.
think I've seen graphs where you measure the atomic and molecular fractions as a function between arms and interarms, and it often.
Yeah, that's right. So this is the measurement in the Milky Way. And yeah, I skipped the details because it's very complex as an introduction. But what we did was looked at H1 and CO data. CO data is from Tom Dame's galactic plane survey. And of course, in the Milky Way, we are inside, so we cannot separate arm and interarm regions clearly. But one thing we realized is if you look through the disk of the Milky Way, and the contours are isovelocity contours in observation. So this line appear as 60 kilometer per second in redshift.
Mm-hmm.
And the problem in the Milky Way is one velocity corresponds to 2 points near side and the far side, and we cannot separate the two easily. So separating arm and interarm region is difficult. But then we realized that one velocity actually corresponds to the same distance from the galactic center. So we don't need to separate arm and interarm or far, near and far sides. We can just calculate the molecular gas fraction at each velocity and then plot it in here. So all these data points represent the entire galactic disk, all the data points of the galactic disk. And we cannot say which point corresponds to spiral arms and which point corresponds to interarm regions, but some of them corresponds to spiral arms and some of them corresponds to interarm regions. And so, and if you look at the width, the main part of the width, it doesn't go down to zero in any data point. And that means even in the interarm regions, the molecular gas fraction doesn't go down to zero. It stays very high, and the change is within like 20% or so.
But I'm remembering you also studied external galaxies. I think that's what you did present in Lyon,
Yeah.
which also showed this.
Yeah, that's right. So M51 also, we can check molecular gas fraction, the same thing, molecular gas surface density over total surface density. And then yes, molecular gas fraction doesn't change much between spiral arms and interarm regions. So there again, if you destroy molecular clouds and molecules and form atomic hydrogen, then it doesn't explain the observation. Again, this is a very simple argument. We just don't see atoms in the interarm regions.
All right, Gina had a question. Two questions, sure.
Have you thought of how can we trace observationally this drift velocity?
Okay, could you speak up?
Oh, sorry. Yeah, I can come closer. So how can one constrain this parameter, the drift velocity, that you input into your model observationally?
That's a very good question. So there's an old study by, I think, Lysowitz from 80s. So they compared galactic molecular cloud and young star clusters, and then measured the velocity difference between the two. And I think they found something like 10 kilometers per second, the typical velocity. So and also there's a recent study by looking at molecular clouds and also the age of young star clusters around it. And statistically, if you measure the distance of young clusters as a function of their distance and age, then you can see how they move away from the parental cloud, assuming that what you see as is a parental cloud. So age versus distance of young clusters, and that gives us the velocity, and that velocity is something like 10 kilometers per second.
Okay. Second short question is, how would the completeness of the CO survey, like if you did a deeper survey and the observation, how would that change the tuning fork observationally?
Yeah, that's a very good question. So I don't know the answer to it, but I think that gives me a good chance to show this slide. So yeah, I've been talking about in this talk. I've been assuming that molecular clouds are discrete entity and never change. But if you think about it, Jonathan, like cloud collision, for example, and then if two clouds collide and merge, or cloud collision splits them apart, or galactic shear splits them apart, then cloud actually evolve from small to large and large to small. And when cloud evolves, what is cloud lifetime? How should we define cloud lifetime? And in this process, small cloud merge becomes massive clouds, and sometimes go beyond detection limit. And Funk's detection limit is 10 to the 5. So what they see is only this phase of the cloud evolution, but it could split apart to smaller clouds and then come up again above the detection limit. In this case, do we want to define this length as cloud lifetime, or this whole duration of the cloud lifetime? That's something that we should think about. My preference is, since we want to know the cloud lifetime at the duration that the gas can potentially form stars. And for that, I think it makes more sense to call this entire duration as cloud lifetime. And probably more appropriate way to call it is the lifetime of molecules rather than lifetime of molecular clouds.
Well, maybe I can add to that. I mean, in the shear-driven GMC collision model that we've worked on, the expected time scale for collisions between sort of equal mass clouds is about 10 to 20% of a orbital time. So in the solar circle, that's 20 million years to 40 million years. It's very close to all these numbers. And once a cloud collides with an equivalent mass, then it sort of resets the clock, if you like, on what you mean by cloud lifetime. So
yeah, that's right. So if you take this short definition as cloud lifetime, and then I think it's what current tuning fork with 10 to the 5 solar mass threshold is giving you is roughly consistent with what Jonathan is saying. So the duration that cloud is above the detection limit seems to be something like 20 to 30 million years, which is the result from the tuning fork analysis on the FANCS data. And that seems roughly consistent with the time scale that Jonathan is mentioning.
But there's two other related points. So when you have a cloud collision, that's very disturbed kinematics. So you can imagine the compressed part of the gas, which is going to form stars, might then have systematically different velocity than a lot of the rest of the cloud. So that could be this drift velocity. The typical collision velocity is the shear speed at the tidal radius. It's actually 15 kilometers a second. So that's a natural way to get a drift speed of order 10 kilometers a second. And then that suggests a test. So we could do tuning fork as a function of radius and see if the time scale that emerges is something like this 10, 20% of the local orbit time. So maybe that should be a next project if we can do that. Just split the galaxy into inner and outer regions and check the time scales. Okay, are there any other questions for Jen or comments? Please, Appa.
I have two questions. First, if the first method of cycling of molecular cloud is right, so how much a molecular cloud can generate young cluster? Like how much what observation is done? Like how much it can cycle?
Oh, so how we can separate the two models? Is that the question?
How many time a molecular cloud can generate young clusters? How many cycles goes through?
Yeah, that's a very good question. I don't know. What I'm saying is, the cloud dies in one cycle is an assumption.
Yeah.
And it can go on many cycles. I think in reality, there must be some gas accretion from the surrounding regions or cloud collision, so the addition of mass, and then also some part of the cloud, get definitely affected by stellar feedback, and we do see some molecular gas being photo-dissociated around H2 regions. So, so I don't think it's that simple if you think about the whole cloud evolution.
Okay, did you have a
But
follow-up?
the answer to your question is, I don't know.
Yeah.
I don't know how many times.
I have one more. I guess I don't understand much with the probability statistics you saw for the star thing. I saw that for the star there's a factor of T over by T gas, but there's no such factor for the gas thing. Is there any reason for that?
Sorry, I didn't really understand that question.
About the probability, but I think it's because that was the aperture centered on the cloud, and so there's always a cloud there, but there's not always a star there. So that's why you have this T over.
Oh,
T.
so this part, okay.
Yeah.
Yeah, so this central cloud, right? So the probability for that gas particle to have a star is T over T gas. That's a probability.
Yeah.
Okay.
Great, and we have a question from Jen.
I have a question.
Oh, sorry, Dave, we'll come to you in a second, but first, Jen.
I'm sorry.
Hi, Jen. Thanks. That was a really nice talk. I wanted to ask about one of the solutions that had been proposed, or at least one of the problems that you wanted to discuss, which is the lack of atomic gas that's detected in the centers of galaxies. And I just wanted to ask if it's possible that H1 is just not in a phase that's easy to observe. So is that something that is generally cited when it comes into these timescale arguments, that H1 can be, just in a different phase. And are those also not detected then in more pointed observations of, absorption against quasars, that kind of thing, or absorption against point sources? Or are you only discussing the H1 that we usually see in emission? Thanks.
Yeah, that's a very good point. And yes, that's right. So there are some ways to hide most of the gas mass in an observable phase. So one is called the neutral medium. If it doesn't emit much 21 centimeter, so we cannot detect it easily. And also we can call for a CO dark molecular gas because we are observing CO in the end. And if the molecular gas is not visible in CO emission, then we are missing it. So if you say that we can hide and we want to hide most of the gas in those two invisible phases, then yeah, we can, it's a game changer. We can basically change the whole thing. So that this discussion is based on what we can see. But yeah, there is a possibility, which I think is still hypothetical. But yeah, it is possible.
Are you saying in the Milky Way that there could potentially be a lot of cold neutral medium that's been missed in the inner galaxy that could change your ratios significantly?
Yeah, so you can double the H1 mass or triple, something like that. You can do that, then yes, it could change the discussion.
Is that reasonable, realistic?
No, so there's not that. Okay, so as Jen said, there are some quasar absorption study to estimate the cold neutral medium phase of H1, and I think I don't think it explains, like, it doesn't increase the H1 mass by a factor of 2 or 3. I think it's something like 30%, 40% at maximum, which doesn't change the discussion.
I remember there were studies of people looking for H1 envelopes around molecular clouds. I mean, again, if you're forming them very quickly from H1, you should see these big flows of H1 that are not seen locally around individual clouds. So that's another constraint. All right, we go to Dave Hollenbach's question now.
Yeah, sorry, I was trying to figure out how to raise my hand, but I couldn't figure it out.
That's fine.
No, I usually can find it on my screen, but it's not appearing. But anyway, my question is that don't you see sometimes young clusters that have absolutely no CO anywhere near them? And why would that be?
Yeah, so we do see, even H2 regions, sometimes you don't see any CO around it. So there must be some photo dissociations. And yeah, young clusters, sometimes we don't see any CO emission around it. So there must be some effect, some impact by photo dissociations. Here, I'm not talking about individual case. I'm talking about the general picture on average. And on average, since we don't see much H1, which should be the end result of photo dissociation. So since we don't see it, it seems a bit difficult to think that the majority of molecular gas get photo dissociated after star formation in short time scale.
Can we pick on some particular examples? So Dave, are there particular clusters you have in mind in the galaxy or nearby galaxies?
No, I just got that impression from the old paper by Blitz and so forth, that they sort of had these categories, and one of them was just, clusters of stars that had no molecular gas anywhere near them.
It could just be CO dark, I guess. I suppose in
CO dark, right?
Well, CO then is an option. But clouds will be impacted by a feedback, so that process will happen at some level. I guess the question is, what Jin and I are saying maybe is it's not a dominant level compared to potentially other processes. I know Inotsuka has told me that he expects clouds to be impacted by supernovae every something like 1 million years. I remember that.
And we don't see that. That's for sure.
But how do we know that, Jin? I mean,
Well, I mean, in nearby galaxies, we see, so I can show you one example, which is our observation. So this is CO120 from ALMA 12 meter, 7 meter, and total power array. The gray scale is CO120, and the detection limit is 10 to the 4 solar masses. So we are basically detecting every single molecular cloud in this image. And if you compare this with H-alpha emission or any other trace out of star formation, there are a lot of CO not associated with any star formation. So I don't think every 1 million years, all these gas can be impacted by stellar feedback or supernova explosions. I don't think that's possible. We just don't see it.
Well, we should redo the calculations of statistics of supernova remnants and clouds. But Dave, are you working on that with Chris at the moment? This global model? Do you have a comment on that?
Say yes. No, we're not looking at supernovas because we think they're insignificant, but we're looking at just the expanding H2 regions around clusters of stars that form in the clouds, and the evolution as they turn into blisters, and computing, how much gas is ionized. And we're not actually looking right now at photodissociation. We're just looking at ionization and then the flow of that gas from the cloud. But we're also looking at the fact that the H2 regions generate shells that get accelerated by the expanding H2 region to escape speed, so that there's ejecta from the clouds as well, which is not ionized. So we're looking at both the photoionization and the ejecta of the materials, but we're getting a fairly substantial amount, and we'll have to struggle a little bit to understand why you don't see more atomic gas. I mean, that's that old problem of Scoville's, and but we're finding that as star clusters form in molecular clouds at the rate we sort of use the observational rates at which stars are forming in giant molecular clouds, we get a substantial amount of destruction. Now, a fair amount of it is this ejection, and of course the ejection could be, like you say, that basically the cloud is being just split up into smaller pieces, that some of which stay molecular. And so we'll have to look at that more carefully.
Great. Well, we'll probably have to invite you, Dave, to give an Origins colloquium sometime in the future.
This is a project that I took on. I mean, I'm obviously retired, and I took it on when COVID started so that I'd have something to do as I was trapped in my house. And that was 2020, and I thought I'd get it done in a year. And so here we are.
Great. All right. Well, we're at the hour here, so I think we should stop now. But let's thank Jin again for a great talk and discussion.
Great talk.
Thank you very much.